All right, so let's take a look at the warm-up. So I am recording this session, so if anybody needs to get to career fair, by all means. But I wanted to go ahead and still have the class. We can get a good review in before the exam. But I will post this on Canvas or YouTube or send out a link or something with a video review. All right, so from the warm-up, we have determine whether or not the following matrices are invertible. And the big idea from 2.3 was this invertible matrix theorem. And I know it's long, A through L. We've hit all these ideas before. That was the big idea. If the matrix is invertible, there is one and only one solution to AX equals B. That gives us existence and uniqueness. Okay? And because it's an n by n matrix, if you have one, like if you have existence, it implies uniqueness. So as we look through all these lists of stuff, we can see the idea that if we have an equation that has only the trivial solution, that's an idea about uniqueness. If we have columns that are linearly independent, that's an idea about uniqueness. If the transformation is one-to-one, that's an idea about uniqueness. So all three of these are really tied to the idea of uniqueness. Okay? How do we tell if any of those things are true? Whether the columns are linearly independent, or the transformation is one-to-one, or there are unique solutions. We're looking at the pivots, and all these guys would be there's a pivot in every column. Okay? And we have a bunch of ideas in here that are about existence. So the columns span the space. It has at least one solution. The transformation is onto. All those are ideas that are related to the existence of solutions. There's always at least one solution, X equals B. And how do we tell that guy? Well, for that one, there have to be a pivot in every row. Okay? And so if we have a square matrix, if there's a pivot in every column, there has to be a pivot in every row. That's what combines these two ideas here. A lot of the other ones are just kind of restatements of these things. So if it's n by n and there's a pivot in every row, that means A has n pivots. That's what C is. Okay. If there's a pivot in every row and column, we'll be able to row reduce it to identity. Okay. If the matrix is invertible, well then there exists that guy and there exists this guy. And the transfer is also invertible. All these really are just built upon what we've already seen before. Okay, so now we look at the first one and say, is that invertible? No, it doesn't even meet the first criteria. It's not square. And you can make a whole bunch of other arguments here. There's a pivot in the first column and the second column, but not the third column. So it doesn't have a pivot in every column. All right, so right away we can look at that and say no. Now we look at the second one. The second one is square. Right, check that first box. Is this one invertible? No, why not? What would be our argument here? How would I determine whether there really was an inverse to this or not? What are my steps? I could always row reduce. I could always say, I'm going to row reduce this guy and figure out where those pivots are. I can always do that. In this case, I could look for something else. I could look at those columns and say, wait a second, if I took the first column plus the second column, what would I get? I would get the third column. Right? If I add the first two, I'm going to get the third one. Well, I can see that by inspection. How would that tell me about invertibility? Well, if I'm just treating them like vectors, right? Like column one here, if I take this column plus this column, boom, I get that column, right? Okay. That's something I just recognize. If you don't recognize it, don't panic. You can still roll reduce and check the pivots. I look at that guy and say, hey, wait a second. Column one plus column two is column three. What does that tell me about the columns that relate to invertibility? They're linearly dependent. They are not linearly independent. Okay, so one of those guys is the columns are linearly independent. But that is not true. That is false, which means all the things are false for this n by n matrix. Matrix is not invertible. So I can say no because columns of A are not linearly independent. Not linearly independent. Okay. All right. Once again, if you don't see that, that's fine. Do the row reduction. You will see that there's not a pivot in every column. Okay. And then we look at the last one. Now I'm looking for anything that like disqualifies it right away. Right? Can I see whether there's dependent? Can I see that any rules are broken right away? And if I can't see that any rules are automatically broken, well then I might want to do the row reduction. I'll take R3 minus R1. and I will get 0, 0, and then I'll get 1 minus 2 is -1. Am I done with the row reduction? Have I gotten to our REF form? No, but I don't need to, right? Because all I got to do get to REF, because in REF I can see where the pivots are. How many pivots do I have here? 3 pivots. All right, so n pivots for this n by n matrix. This one is invertible. So yes, it is invertible. All right, any questions from the warm-up? All right, cruising right along then. All right, so I got some questions from the homework, so I just kind of wanted to go through a couple of these real quick and talk my way through them. One of the questions that people struggle with this one, it says, here's a matrix A, construct a 4x2 matrix D using only 1s and 0s as entries, such that A times D is the 2x2 identity. And it says, is it possible for C times A equal to a 4x4 identity for some 4x2 matrix? Okay, and there's not some sort of magical thing for this guy, right? When I'm looking at this, I'm saying, okay, I got to find a matrix D, so that A times that matrix D gives me the 2x2 identity, right? Just knowing that, I should know the dimensions of this mystery matrix. Right, over here I have a 2x4, over here a 2x2. What matrix, what are the dimensions of the matrix go in between here? 4x2, right? It's got to be a 4x2. So I can draw my little picture here. 4x2. And then I'm really just trying to find something that works. Okay? And the way I'm looking at this is maybe from the idea where I use multiplication, I can take a linear combination method. So if I had a matrix times the first column of this matrix, it should generate the first column of the product. Okay? And the number here would tell me how many of the first column of A to use. I'm going to use 0 of those. I'm going to use 0 of the next one. Right? I'm trying to get a 1 here, so I will use 1 of that third column and 0 of the last column. Okay? I'm kind of looking at the matrix and saying, hey, I want to get a column that looks like 1, 0, and another column that looks like 1, 0. Let's use 1 of these and none of the rest. That's really how I discovered my first column. Okay. Use that same idea. What should I use for the second column? Right, 0, 0, 0, 1. That guy should work. Okay. All right, so then it says, is it possible that C times A is the 4x4 identity for some 4x2 matrix? Okay. All right, well, let's flip this around now. 1, -1, 1, 0, -1, 1, 0, 1, like this. Okay. All right. Now I have a 2x4. I'm trying to get to a 4x4 matrix over here. So what are my new dimensions? So now I got a matrix over here. How big does the matrix C have to be? All right, it's got to be 4x2. All right. Now I got a 4x2 matrix over here. Okay. I'm trying to generate a 1 in this position. So this is what I want my matrix to look like. Okay. So if I take this times this, I need to get a 1 here. All right, so I guess I'll put a 1 there and a 0 there. And then the rest of the way, so now I got to get a 0 here. So I guess I could do maybe 0, 0 the rest of the way. That should give me the rest zeros. And then I look at the next piece here. And if I do that, I'm going to be out of luck. Okay. This is what I want to do here. All right. Okay, so the bottom line is we can't, right? So you can keep trying and you can't do it, and I think we're going to leave it there. Okay? All right, a little anticlimactic there. All right, so then it says, the next one is the question for the pre-assessment. It says A times B is equal to identity. then what is A inverse? And I had a lot of questions at the pre-assessment about this one, and that's good, because the pre-assessment was wrong about this one, okay? All right, when you look at this, say, okay, if I have A times B is equal to the identity matrix, then what is the inverse of A? And you want to say it's B. Right? That makes sense. It's the matrix that you multiply A by to get to identity, okay? But is that always the case? Not necessarily. So really, it should have been not necessarily here, okay? So we don't know. We would have to know that B times A is also equal to the identity for B really to be the inverse matrix. We basically have that case in the first thing here. We had A times D was equal to identity, but D is not necessarily the inverse, okay? So really, it was a poor statement. If I said that A and B are both n by n matrices, and that's true, then I can make that claim, but it didn't put that restriction on there, okay? So I'm going to go through and regrade those. So everything should get marked correct for that one, okay? Any questions about that one? All right. All right, plan from attack for today. Answer a couple questions of the pre-assessments. There was one error on the practice exam, kind of a numerical error. 1 times 2 ended up to be 1 or something like that. Right, so I'll point that out. One homework question, the condition number problem from section 2.3. And then we'll follow through with the course review. All right, any questions about what we want to do? All right. So yeah, this question from the 2.3 homework. And it's a really good question. It's a really interesting question. It's just hard to calculate this question for us, okay? So the idea was they have two systems here, and they look very similar to each other. Okay? They look very similar. So specifically, the left-hand side for both of these is exactly the same. And the only difference is the right-hand side, okay? And it's really only almost a rounding difference between the right-hand side. So it says, go ahead and solve the first system, you go through solve this system, and you find some values. And then you solve the second system, and you get solutions for that. But the solutions are very different. Like, whoa, is that okay? Is that all right? That I made this little change in B, and it really changed my solutions, right? And that doesn't seem very good, because the idea is that the difference on the right-hand side is basically a rounding error. It's basically a measurement error. How closely can you measure whatever this value is on the right-hand side? If you're using a ruler, you're not going to be able to get 3 decimals of accuracy, so you're stuck with using 2 decimals, and now you've really changed your solution. Okay? So what's going on here? And the basic idea is that if we looked at the matrix that's associated with the system on the right-hand side, we're looking over here, our matrix is going to look like 4, 2.1, 4.2, 2.2, like that. We say, well, if we were to do the row reduction on this, if we were to row reduce it, the idea is this one would almost be singular, right? So jumping all over the place here. Okay. The matrix is not invertible, but it's almost invertible. Okay, and the fact that it's so close to being invertible, but not invertible, kind of throws up our solution. It is invertible, but it's so close to being not invertible that's what's throwing off our solutions. Okay, and so the idea is we need a way to measure this for a matrix to know how much we can trust in our solution. Okay, so in a more advanced class, we're using numerical techniques to quantify how close it is to being not invertible with something called the condition number. And we're kind of asking what that condition number is on the bottom. The only problem with the question is that they didn't also tell us how to calculate the condition number. Okay? And there's actually a command in Mathematica that will say condition number, boom, and it'll kick that guy out. But there are different ways you can compute a condition number, and the way they're doing it in my lab is different than the way they would do it in that software, right? And so you actually get a different value. Okay, so I'm going to go through and modify the grade for that last one, so the bottom line don't stress about that last one. But I still like having the question on the assignment because it's a real problem you might run into. Even if a matrix is invertible, right, you can have special matrices that are so close to being not invertible, that it kind of messes up your solutions. And so the condition number is one way we can quantify how much we can trust our solution. Okay. All right. Any questions there? Okay. All right, I am already feeling the pressure of time here, so I'm going to launch through to the review portion of this guy. Okay. All right. So we have, 35 minutes to review all the content we've learned in the course so far, right? So the idea with the review is it's not going to reteach everything. We're going to hit the high points. The value of the review for you should be if we're covering a topic, you say, I have no idea what he's talking about right now. You have pinpointed something you need to review. That's really the goal of a review process, okay? All right. So in the first few sections of chapter 1, we were introduced to the basic definitions of linear algebra. We learned that linear systems could have either 0 solutions, 1 solution, or infinitely many solutions. And we could create an augmented matrix and use row reduction to find solutions. And we saw over and over again that to answer lots of different questions, row reduction was the process. So go ahead and show me your row reduction. Here is a system. Create the augmented matrix. Write the solution in parametric vector form. And then put your answer into learning catalytics. This is your first question. Cool, maxing out at 55 students, 21 responses so far. right, 59 students, 45 responses so far, 28% correct. All right, let's take a look. So far I have done my augmented matrix, and I've started to go through the row reduction process. I did 2 steps here in this first one to get to this phase. Another 2 steps to get over to here. At this point, what form am I in? REF. I can identify my pivots. I say, yes, there are solutions. How many solutions are there? Infinitely many. I have one free variable. There's no pivot in the far right-hand column, so I have infinitely many solutions. I finish up my row reduction over here to get our REF, and now I have to write out my solutions in parametric vector form. So I take the first row, and that basically tells me that x1 plus 2x2 is equal to 0. I look at the second row, it tells me that x3 is equal to -1. That's all I got. There is no x2. What does x2 tell me? That's free variable then, right? So now I solve for x1, x2, and x3. Get my solution in parametric form. This is minus 2x2. x2 is free. x3 is -1. Written as a vector, I would have a vector of constant stuff that would look like this, and a vector of x2 stuff that would look like that. And that should be my solution in parametric vector form. Any questions so far? Any questions about that process? Under 50% correct. What questions? Little computational problems? Yep. Right, so the in-between steps would look like this. Remember, I'm trying to find a solution. My solution will be a vector whose components are x1, x2, and x3. And this is what my solution is going to look like. So when I solve for those values, I'm just going to throw those into a vector. All right, so -2x2, x2, and -1. Okay. Now, when I look at those, I have some things associated with x2 and some are constants. But I want to kind of visualize them all as having each of those pieces. So it's kind of like 0 minus 2x2, and 0 plus x2, and -1 plus 0x2, right? That's what I'm maybe mentally doing. And then I'm saying, oh, that looks like the sum of 2 vectors, right? And the right vector will have an x2 in each component. All right. Any other questions? All right. All right. So we had infinitely many solutions. We kind of know why. We were looking at the pivots, and those really help us determine that. And so now, and generally learned we have 0, 1 infinitely many solutions. How can we tell? There are no solutions if the right column of the augmented matrix is a pivot column. If the far right column is not a pivot column, then the system is consistent. There's some of our vocab. Consistent if there are solutions. A consistent system with free variables has infinitely many solutions. And the non-pivot columns of the coefficient matrix identify free variables. Okay? That's all the words. Right? And the question is, can we interpret those words, actually look at systems, say, what's going on here? So if I look at that first matrix on the far left, I will send you the next deliverable that says, how many solutions are there? 0, 1, or infinitely many for that far left matrix. All right, we got 63 students, 53 responses, 95% correct. That's pretty solid. We saw that there is a pivot in the far right column. There is no solution. And why, once again? Because if I wrote out the associated equation, it would be 0x1 plus 0x2 plus 0x3 plus 0x or somehow equal to 2. That can't happen, right? That's why we're very strong on that question. So what we'll do for the next two, we'll look at this one and know how many solutions here. Infinitely many. Pivot here, No pivot here, so there are solutions. No pivot here, so there are free variables in any. Over here. No. So is there a pivot in the far right column? No, so there are solutions, right? 0 can equal 0. Yes, that's true. 0 equals 0. That's true. Okay. This row would tell me that negative x2 is equal to 0. That's perfectly valid, right? There are solutions here. How many? Are there any free variables? No. If here, so x1 and x2 are both basic variables. So there's only one solution for that system. Okay? We can find that solution if we wanted to finish up the row reduction, right? So if I did R1 plus 3R2, 0, 0, 0, 0, 0, 0, 0, negative 1, 0, 2, 0, 2, right? Divide the first one by 2, multiply the next one by negative 1. I didn't put this system. The solution would be 1 is 1, 2 is 0. That's it. All right. Any questions there? All right. So after that, we added some more vocab or review of the vocab we talked about. A consistent linear system has solutions. Inconsistent has no solution. Right? Row equivalent matrices. That just meant that we were doing row operations. And that changes the system, but it doesn't change the associated solution. That's why we can do row operations. Get to the end and say, hey, these solutions also apply to the original system. Those ones are row equivalent. We know what REF is, our REF is, pivot positions are. Any questions about the vocab kind of through that part of the course? Yep. You just have to use it, right? So the previous questions would identify the pivots. Well, you got to know what a pivot is, right? So you got to know what that vocab is to do it. It could say, are the following matrices in REF or REF, right? It could just come up in like a true or false or fill in the blank where it says a system with 3 variables is always consistent, right? If you don't know what consistent is, you can't answer that thing, right? So you gotta understand all the vocab. This is a language course, right? All right. Any other questions? Yep. That's where, so it might identify the pivot positions, right? And those would be the 2 pivot positions. Here the pivots would be here and here. Here the pivots would be here, 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 and this last one, right? That is a pivot. Far right column, that is a pivot, okay? Those are all my pivot positions. And you might also ask, like, if there are solutions, you know, what do they look like? Is there one solution? Is it a line? Is it a plane? All those kind of questions would apply. Now, depends on the space we're working with. So if it was a 4x4 system, I guess you could say that because that is one free variable, if there were solutions, it would be a line in our 4. But generally, I'll ask that for a 3x3 system or a 2x2 system. All right. All right, so after that, we talk about vectors, right? We did also the calculations of matrices and vectors. We have 2 matrices, 3 matrices, a whole bunch of vectors. We got to make sure we can do all the basic calculations. So go ahead, calculate what you can, and say I can't if you can't, right? Or say NA if you can't. Go ahead and do these calculations. I do not have this as a deliverable, so go ahead and just write them out, and I'll work through them, and we'll compare answers, and we'll go from there. Hoping this video works for the career fair people, but I know that I walk over here and the audio is going to drop out. So I don't know if I should mess with them and just be like, now we're going to look at this thing over here. Okay, let's look at those first ones real quick. Any questions about those kind of core calculations? Any questions here on those first 5? Any questions about the first ones? Yep. So the first one was 2 times the vector v. So here's my vector v over here. I multiplied it by 2. I multiplied the components. Is that right? A times v. So I got A over here. I got v over here. Almost think about the dimensions, right? This is a 2 by 3, and this guy's a 2 by 1. Good. Yeah. This guy right here. First one, that guy should be B. Right. There we go. Sorry about that, right? Sorry. All right. Okay. More things we know how to do it, so that must make more sense, right? All right, okay. All right, so any other questions? The rest of these calculations look good? Okay. All right, the last one's kind of a notational piece here. We have B, or capital B times X equals the vector B. If I wrote this out, it would look like 1, 3, 0, 2. It looks like X1, X2 somehow equal to the vector 1, 2. It's like our matrix equation. The matrix times the vector 2 different ways. I could go up here and rewrite that by doing the row vector multiplication and say this is really that row times that vector to get x1 plus 3x2. I do the same thing for the second piece to get 0x1 plus 2x2. And if those two vectors are equal, the only way those vectors can be equal is if the components are equal. And that tells me that that matrix equation is the same thing as that linear system. And then I could do that multiplication using the linear combination vector and say this matrix times that vector can be written as x1 times the first column plus x2 times the second column. And that's supposed to be equal to the vector 1, 2. And that's the vector equation. So the big idea was they're all pretty much the same, right? And that's where we kind of ran from that. Along the way, we got a little vocabulary. Linear combination is adding multiples of vectors together. So that first question, 2v plus b, is an example of one linear combination. Okay? And the span will be the set of all possible linear combinations. So for this case, this result for any value of x1 or x2 would be the set of all linear combinations. The span is the set of all linear combinations. Okay? All right, so now we see those equivalencies. The big idea was that a vector equation and a matrix equation are all just really representations of the same thing, and we solved them all using an augmented matrix and row reduction. Okay? So your next task would be to rewrite this in all these forms. Okay? So here's our system. Write the matrix equation. Go ahead and write the vector equation. I'll give you a minute here. You can write those guys down so that we're happy with the different representations. So I have my representations up there. We said these are all the same thing. We would solve them all by creating the augmented matrix and doing the row reduction. But this is also the first opportunity for us to get mixed vocab. We might say, solve ax plus b, right? Ax equals b. Whereas for the vector representation, we might say, is 2, -1, -1 a linear combination of the vectors, right? Or we might say, is this vector in the span of those vectors? And that all meant the same thing, right? Whether we asked it, is this vector in the span, or we said, solve the system or solve the matrix equation, is all basically meaning the same thing. We have to find the x that satisfies the equation. Any questions there? And that was a specific question for this equation. But then we said, this is really the core idea, that matrix that really drives the system. We might end up changing B. So the next question we might say is, what about the matrix A allows there to be solutions or not be solutions? And could I broaden that question out, saying that would I be able to find solutions if I change the value B? And so we might say, is there a solution to AX equals B, right, for any B, in this case in R3? It doesn't matter what B is. Will there always be a solution? Or do the vectors span R3? So the questions are similar, but they're more general. They say, can we do this for any B that we could possibly put on that right-hand side? Okay? And so this was our idea of existence and uniqueness. So we wanted a way to determine whether we could always exist in a solution, and so whether solutions were unique or not. And the idea was we could look at the pivots to determine that. So how do we know when there always existed a solution regardless of what we put over here on the right-hand side for B? Well, the idea is that far right column could not be a pivot column. Could not be a pivot column. And so we looked at it and said, well, if there was a pivot right in front of all those values, if there was a pivot in every row of the coefficient matrix, it doesn't matter what B is. Is there any way there could not be a solution? No. So if there's a pivot in every row, there would always be a solution regardless of what B is. Okay? And the other one is for uniqueness. Well, what brings us that infinite many solutions? For those free variables. So if I had a different system here, and I have my vector B over here, there could never be free variables if I have a pivot in every column. Okay? So in this case, I could not have more than one solution. It would be at most one solution. Here, there will be at least one solution. It's all based on the pivots. All right, so we can summarize that information as follows, right? There will exist at least one solution to Ax equals B if there's a pivot in every row. There will exist at most one solution to Ax equals B if there's a pivot in every column of the matrix. Any questions there? All right, then go ahead and check this one. This one is a deliverable, so there you go. Does there exist a unique solution for that matrix A? 64 students, 41 responses, 63% correct. All right, so we take a look at it. We have to do a little bit of work. We have one row reduction step here to get to this form. Now I see there's a pivot here and a pivot here. So that means there always will be solutions. If I augment here with B, and this is just my matrix A, augment with B. There's a pivot in every row, so there will always be a solution. There's at least one solution, but there's no pivot in this third column. And if I will have a free variable, there will be many solutions. Okay, so I do not have any. So there is at least one solution, but there is not at most one solution. So this would be A. I have existence without uniqueness. Any questions there? All right, and then along the way, we added some more vocab. Linearly dependent and dependent vectors, and homogeneous equations. We had all those things. We had a homogeneous vector equation which looked like this: C1V1 plus C2V2, C3V3 equals 0. Right hand side was 0, then we had a homogeneous vector equation, or a homogeneous matrix equation. And we used that equation actually to define linearly independent. We said that the vectors V1, V2, and V3 were linearly independent if and only if the only solution to that vector equation was a trivial solution. The only solution was C1 is 0, C2 is 0, C3 is 0, then those vectors are linearly independent. That's the way we defined linearly independent. Any questions about that guy? Now, if there's only one solution to this, could there possibly be three variables? There could not. So the way we could actually show this was true, show they were independent, is to put V1, V2, V3 into a matrix and row reduce. And there should be a pivot in every column. Pivot in every column tells us not only that there would be at most one solution, but it would also tell us that the vectors are linearly independent. All right. So after that, we got into the language of transformation in sections 1.9. Transformations. We talk about transformation, take vectors from one space and map them to another space. We learned a bunch of vocabulary about transformations, and also the big idea that every linear transformation from Rn to Rm could be expressed in terms of matrix multiplication. Okay? So we had spaces, we had mappings between this space over to this space, right? X is our input, B is our output. Okay? This space, the set of all possible inputs, was called what? The domain. This spot over here, where the outputs lived, was called the codomain. This spot over here, just all the B's you can actually get to, all the images, that was called the range. Okay? Sometimes the range was equal to the codomain, sometimes it was not. Okay? So we have some vocabulary there. And so we might look at a problem that transformation takes x's and maps them to b. And that's what our matrix equations really did. So if we have this matrix equation, okay, we would say the domain of this matrix equation, this transformation, would be what? The domain of the input is what x is I'm putting into the process, right? So my domain is going to be R2 here. My codomain is going to be R3. My range is not going to be R3 because I actually can't get anywhere everywhere over here. Right? So it would just be a linear combination of these two vectors that I can get to in my range. Okay? All right. So this transformation would be a mapping from R2 to R3. Okay? All right. Any questions there so far? Okay, and so then we had a way to generate the appropriate matrix. If we gave this transformation words, we should be able to generate that matrix. All right. And the way we did that is by transforming the columns of the identity matrix. Go ahead and take a second and see if you can generate the matrix associated with this transformation. Can you find the matrix that does this transformation? Ooh, that's my next question. Deliverable, there you go. All right, I did the formal work there. There's a lot of quick responses. I'm assuming a lot of you just wrote that guy in. That's fine. That trick always does work. This is the formal process where we're transforming the columns of the identity matrix. Okay. Any questions there? All right, then we had a whole new thing of language for transformations. Unfortunately, we don't say, is there always a solution to the transformation equation? That's not really what we say. You don't say is there always at least one x that maps to b is what we basically say. Instead we say that if the transformation is onto, if for every x there is an x such that t of x is equal to b. Okay? So onto is really the same thing as saying that there's at least one x for every b. Okay? It's the same thing as saying there will always be at least one solution. So if I took a transformation and I generated the matrix, the transformation would be onto if there was a pivot in every row of the matrix. If there's a pivot in every row, there will always be a solution. Okay? And then similarly, we don't say our solutions to Tx equals b unique. Right? Well, unfortunately, we don't use that language, but this is basically what it means. We say if the transformation is 1 to 1, and for each b, there is at most one x that maps to b. Okay? So the idea of 1 to 1 is the same thing as uniqueness. And so if we had a transformation, we could generate the matrix. If there's a pivot in every column, the transformation would be 1 to 1. So we had that vocab for our transformations. So P being onto, and there was always a solution to Ax equals B, which is true when there's a pivot in every row. P being 1 to 1 means the solutions to Ax equals B are unique. That's true, there's a pivot position in every column. Those are the big ideas. The magic happens when the transformation is both 1 to 1 and onto, and the transformation, as well as the associated matrix, is invertible. Okay? So we say, well, when is the matrix invertible? Well, you got to have a square matrix. There has to be a pivot in every row and every column. Right? It's only happen together as n. The transformation has to be onto and 1 to 1. Right? The columns must span the space and be linearly independent. Okay? And the matrix must row reduce to identity. So those are all the things from the matrix inverse theorem, essentially, we talked about at the beginning. All right, so lastly, we got to be able to calculate these guys. We kind of hit that formula up last time for calculating the inverse. So we should be able to calculate these. You can use the formula for this first one. Can't invert that last one or the second one. And for the last one, to calculate the inverse, we would augment with identity like that, and we would do our row reduction. So in this case, I do my row reduction. I would take R3 plus R1. I would get 0, 2, 1, 1, 0, 1. And then I would do a couple more steps like that, right? Doing the row reduction. And I would end up with this. I would end up with 100010001 augmented with 1 negative 20010 and 1 negative 21. So I would row reduce, and the left-hand side would turn into identity, and the right-hand side would be that inverse. Okay? And the last thing is just, can you use the inverse to actually solve problems? Okay? So if I had a problem that was like this, if it was here's A, here's B, using the inverse, I would just take my inverse value and multiply by B. Okay? And there will be a question on that exam that says, solve this equation using the inverse. If you don't use the inverse, use row reduction, that will be marked wrong, right? You got to make sure you calculate the inverse and then multiply both sides, so basically inverse times B. That's how we use the inverse to solve the equation. All right, that is all I got. Exam on Monday. Email me if you have any questions.